going to make the code available on GitHub after the talk. It's, the link to the repo is there at the top. The code isn't available there yet, but you don't really need it for the talk because you're going to have to download a couple of quite large files if you want to run the notebook. So running them alongside the session would be kind of pointless, but it'll be there straight after the talk. You're going to need 3 CMB maps from the Planck experiment, 1 foreground map and 1 power spectrum, but we're going to get into those a bit more detail later. So welcome to a beginner's guide to data analysis in cosmology. I'm going to provide an introduction to data analysis in cosmology, show you where to get the data, give you some examples of using the data using some well-known Python packages, and then we're going to discuss some of the routines in those libraries in a bit more detail, the ones that I'm going to use specifically for CMB analysis in this talk. So firstly, can everyone hear me? Would anyone like me to speak louder? So at the moment I'm a former cosmologist, and currently I'm an ML engineer at Argos. And so cosmology is something I did quite a few years ago now. I finished my PhD in 2013. So recently I've started looking at some of these data sets using Python packages, which have been developed over the last few years, and actually give you a really easy way to start looking at some of this data. So I'm going to start with an introduction to the Fourier transform, just briefly, because it's a really important technique in signal processing and cosmology, and many other fields. And in cosmology, it's used to calculate the power spectra of signals. And by that I mean we're looking at how power is distributed into different frequency components of a signal. And by using Fourier transform, we're going to be able to make some complicated problems easier by transforming to Fourier space. And I'm going to go over that in a bit more detail later. So what's the Fourier transform in kind of 4 lines? Any continuous complex function can be written on minus infinity to plus infinity, can be written as an infinite sum of plane waves. And so we can write any continuous function as a sum of cosines and sines. If you haven't done Fourier transforms before, that's all we're going to need for this talk. We're going to look at how to break down signals into frequency components. So all you need to think about is the way that you break down a signal into a sum of trigonometric functions. However, in experimental situations, we don't have continuous functions, and we've got finite intervals, and we're sampling them at discrete locations. So in this case, we use something called the discrete Fourier transform. And if you take a simple signal, a simple sine wave, and you sample it 10 times, you're going to get a vector, y sampled at 10 points, and that sampling is taking place over a period L of that signal. And you're going to be sampling that signal at intervals of delta t. So you're going to have a number of signals in a function, which can be broken down into components like this. And if you've got a signal of twice the frequency, you're going to see something like the right-hand plot, which is the same sampling rate. So you've still got 20 samples, not 10. But you've got twice the frequency, so you can see that if you wanted to reproduce that signal from those 20 points, you would then reproduce a signal which is 2 times the frequency. So the discrete Fourier transform is an equation that tells us how to break down a signal into frequency components. Please stop me at any point if you want to ask a question. And so that formula for discrete Fourier transform is a sum over the length of that vector. So we've got n samples, so we've got yn, and then we multiply by the factor e to the minus 2 pi I k n over n. And that gives us, you don't need to worry about this too much, but what we're doing is breaking down the signal into a vector. We're transforming from We're transforming a vector of n complex numbers, yn, into another vector of complex numbers, yk. So we're starting with a vector in real space, and we're transforming it to a vector in frequency space, yk. I'm going to show you how to do this using the FFT-pack library. So the inverse discrete Fourier transform does what it says. It takes the inverse transform from frequency space back to real space. So we go from the vector yk in frequency space back to real space and back to the vector yn. Now, this is actually implemented through an algorithm called the fast Fourier transform, because the discrete Fourier transform would be naively an order n squared calculation, but the fast Fourier transform takes advantage of the repeated calculations that you're doing to speed up, and you've got an order n log n calculation. And this is like the algorithm that's implemented in FFT libraries. If you want to do some reading about the original algorithm, then I'm going to put this link in the code that you can download this code later, and all of these links will be available. So let's look at one example of practically how to calculate the Fourier transform of a signal. So what I've done here, sorry, this is a bit small. On the top you can see 3 different arrays. On the left-hand side we've got one point here on the top left. So this is, the top row is an array of just 1s and 0s. So what we've done is place a 1 at position 0, 5 in that array. So this at the top is frequency space, and we've taken the inverse Fourier transform to go from frequency space to real space, which is on the bottom row. So the Fourier transform of that inverse Fourier transform of this graph gives us this plot here. So you can see that we're getting what we expect, which is sine function, and it's oriented depending on where you place that point in frequency space. So you can take this library and play with it yourself and see for some more complicated examples what happens. The reason why I started with looking at the Fourier transform is because for CMB analysis it's really important. So I'm going to show you a graph later on of the CMB power spectrum, and we're going to come back to this theory a bit later on. So what's the CMB? It's a uniform anisotropic field which was released about 300,000 years after the Big Bang. And today we measure it at a temperature of about 2.72 Kelvin, so just above absolute zero.
What does it stand for?
The CMB, sorry. So the cosmic microwave background. So it's this radiation that was released when, they were in the early stages where you had a plasma. So at that point, electrons and protons, at 300,000 years after the Big Bang, electrons and protons could recombine and form neutral hydrogen. And up until that point, radiation was coupled with matter, so it couldn't stream through the universe. At that point, the radiation decoupled and it streamed through the universe, and that's the radiation that we're now measuring, which has, since then, it's being cooled to 3 Kelvin. So there have been a lot of experiments measuring this radiation, and it's a really interesting problem in data analysis, because the fluctuations in this field is of the order of 10 to the minus 5 Kelvin, and there's a very low signal to noise ratio, so you can imagine that any noise in that signal from the galaxy or from your instrument that you're measuring the sky with is going to create noise that you have to remove before you can observe the CMB. And in particular, ground-based experiments have very large arrays of thousands of detectors sampling large fractions of the sky, creating very large time streams, and those time streams need to be processed and turned into maps of the sky. I'm going to show you now some easy routines that you can use in Python to visualize this data. So this first example is an example of using the healpy library. So if you download this data set, you can use the healpy read map function to read in one of these data sets, which is in a FITS file format. And you can then look at this using the molview function. So you can, this Planck IQ is just an array. So we can view that array using this function. And we can set the minimum and maximum temperatures. Sorry, this is really hard to see, isn't it? Can I zoom in? So we can set the minimum and maximum temperatures, and these temperatures are measured in Kelvin. So that's 300 microkelvin, plus or minus 300 microkelvin. And if we look at this map, you can see a series of peaks, which are roughly plus and minus 300 microkelvin. So this is of the order of 10 to the minus 5 Kelvin. So these are tiny temperature fluctuations. But you can see some really interesting structure in this map.
So what would be base, the K?
Would be Kelvin, which is...
Yeah, but what is that? Is that 0 Kelvin, or is that...
this is fluctuations around 2.72 Kelvin. So this is centered on the temperature of the CMB, and it's just the plus and minus fluctuations.
Okay,
yes. Okay, so a couple more links here for you to get some data sets. And you're going to find that this data is in FITS file format, which is the cosmologist's favorite file format. But these packages work with those files. So this read map function reads one of these FITS files. Okay, so I said that that map showed some interesting structure, and we're going to think about how to describe some of that structure. But first we need to understand how to describe this random field, which is spanning the celestial sphere. So we can think about this map as just an array, and this array is, each element of this array is a sample of a position on the sphere. So if you think about the sphere in 3 dimensions, we're looking out at in different directions, and we're measuring a continuous random field on that sphere. So we can't we measure that using an experiment, and we then sample that field onto a vector, which is this array Y, where n is the number of pixels in the map. And now the CMB is actually, because the initial perturbations were approximately Gaussian, the CMB is going to also be close to a Gaussian random field. So this field should have a Gaussian distribution, so the familiar bell curve or the normal distribution. So actually that vector should be a multivariate given by this function. So let's take a look at that and see if that's true. So we can just plot that as a histogram, plot the array, and we can also fit a Gaussian to it with parameters mu and sigma. And if we do that, then for this Planck data that we've looked at, we can see that this data is very, very close to Gaussian. And again, the units here are Kelvin. Okay, so we've got this data set, but now we want to start doing some cosmology with it. We can now make use of another Python package, which actually we can use to predict what this field should look like given some initial conditions. And it's a really useful package called CAM. So if you can imagine that we have a cosmological model which is described by a set of parameters, and we can then, given that model, we can evolve those initial conditions, and we can then predict what this predict what the CMB would look like. If you want to have a look at this package, then have a look at CAM, and it's called Code for Anisotropies in the Microwave Background. And it's a Fortran library which has this C interface now in Python, so you can pip install CAM, and then you can get access to this code. And I'm going to show you an example of how simple it is to use this library. So we can create a set of parameters. You don't even need to set the temperature of the CMB. I've just done that so that I can use it later on in one of my plots. All you need to do is, on that object which stores your parameters, you can call set cosmology, and then give it, I'll explain what L is later on, but you just need to set your initial parameters. This is what those parameters look like, and you can see that using the default parameters is a lot simpler than going in and setting all of these individually. We can do a quick validation to see that they make sense. And if you want to test your own cosmological parameters, you can go to this website and change those parameters, and it will produce for you several output files that you can save and then import into Python if you want to use them for your analysis. So from this library now we can get the something called the CMB power spectra, and I'm going to explain what the CMB power spectra is later on. Okay, so I've taken some data from the Planck website just to have a look at what this power spectrum is and compare it to the results of CAM. And if we plot these power spectra, we get something that looks like this. The one that I produced using my possibly naive default parameters is the black line, and the Planck best fit data, so this is the theoretical parameters which best fit the Planck, I think 2015 data, is the red line here. The differences are due to the fact that the parameters which I've set are probably different to the best fit parameters from this data set, but they're quite similar, and that's quite nice to see. We're going to come back to this later on and explain it in a bit more detail. But on the x-axis here you can see something called L, which is, I'm going to go into what this is now. And on the y-axis is something called the power spectrum. So we're going to now relate this back to the Fourier transform and think about how L corresponds to scales on the sky. So what we need to now look at is something called the spherical harmonics, and these are the first few spherical harmonic functions. They're quite scary looking, but if we plot them, I'm going to plot them in a minute, but what we're going to do is see that we can break down the temperature into a sum of these spherical harmonic functions. And this equation here, you can see we now have something very similar to the Fourier transform, where we're breaking down a signal into a sum of functions, and we're weighting those functions by an amplitude, which is A. And this is the analog of Fourier decomposition in flat space. So in flat space we have Fourier transforms, and if you're describing a field on a sphere, then you need to use spherical harmonics. And the L in that equation is related to the angular scale in the sky, so it relates to how the angular scale of those fluctuations that you're seeing. And M is related to how those modes are orientated. So we're going to have a look at these functions now, and then come back to this. So there's some code here to plot these functions, which I've taken from a book, an online book. and we're going to take a look at these. So the first spherical harmonic is just a constant. It doesn't have any angular dependence, so it's just a very boring constant. If we look at the first one, things start now to get interesting, and we can see that the first spherical harmonics have two values of m, and this first one is here and the second one is here. So you can see that m is related to how these modes are oriented on the sky, and L is related to the angular scale of those fluctuations. So here an L of 1 is corresponding to large scale fluctuations. So if we look out at the universe, we're looking at large scale fluctuations of 180 degrees apart. As L gets higher, we're looking at smaller angular scales. So if we plot the second one, we see those different modes, again, different orientations, but we can see that as L increases, the angular scale of those fluctuations gets smaller. And what we're going to do now is see how we can use these spherical harmonics to make, recreate the CMB. And someone has created these lovely animations, which we're going to have a look at. So those spherical harmonic functions in this visualization, you can see, if we just wait for it to restart. Okay, so we're seeing those large scale fluctuations, and if you add smaller and smaller angular scales, then you add up those spherical harmonics with different weightings, and if you add up all spherical harmonics with weightings that look like this function on the top left, then you get something that looks like this plot on the bottom. So this is how you create the CMB from spherical harmonics. Okay, so let's think, how is L, which was on that plot I showed you earlier, related to theta? And L of 200 is roughly 1 degree on the sky, and the full moon, if you view the full moon from Earth, that's about half a degree, to give you an idea. So let's go back to that plot and look at, now here, if you look on this plot at scales of about 1 degree, which is L of 200, you can see that there's a lot of power on that angular scale. So the power spectrum here is telling you how that signal can be broken down into frequency components. We're just now working on a sphere instead of on a 2D plane. Okay. So one more thing that we need to know before we can calculate the power spectra from some real data is what's one of the most important instrumental effects that we need to think about. And Fourier transforms, one of the useful properties is that you can convolve a signal with convolve two functions in Fourier space as a multiplication. So we're going to look in frequency space, we're going to model what a telescope beam would look like as this function here, which is a Gaussian, and then we're going to plot that below. So this for a beam size of 30 arc minutes, which is half a degree. If we look at what our telescope beam would look like, it would look something like this. So when we look at this, when we measure the sky with a telescope, what we're actually doing is observing the CMB through a lens, which is therefore a convolution of the sky with an instrumental beam. So in Fourier space, we can multiply those two functions together, take an inverse Fourier transform, and come and get a smooth version of the sky. Okay. So what I'm going to do now is look show you how you can now use some libraries to calculate the power spectra of these data sets. So what you can do is use the healpy library, and what we're going to do is compare the CMB with a white noise array. So what I've done is create just an array of white noise of the same length as the Planck data and plotted that. So here you can see a white noise map. This is clearly very different to the map I showed you earlier because we don't see any structure in this map. And if I plot a histogram of those points as I did earlier, we can see that again we get something which is a Gaussian distribution. So why in one map do we see structure, in another we just see noise when they have the same distribution? This is when we need to go back to that power spectra and think about the frequency components that make up that signal. And we're going to do that in a minute. So we've got white noise, and we've got, I've plotted here the histograms of those two data sets now on top of each other just to show how similar they are. Now let's go back to the Planck temperature map. Why do we have structure in one of these maps and not in the other? So let's look at this power spectra in more detail. So this power spectra I downloaded from the Planck website, and I've just plotted it. And again, this isn't a log plot now, so those peaks look to be in different positions. But this first peak here is that peak at 1 degree on the sky, which is where we see the most power in the map. And if we look at the CMB map, you can see power on that map on scales of 1 degree. So this is how you can think about that transform from Fourier space to real space. And white noise has, so this, I'm going to now plot the power spectrum of that white noise array and compare it with the power spectrum of the Planck map. And so we're going to see the differences in terms of why in one you see the structure and in the other you don't. So on this graph here, we've used a function, called anafast, which is in the healpy library to go from a white noise array to a power spectrum. So this is a really easy thing to do in Python now, and you can then apply some scaling factors and plot this, and we're going to compare it with the theoretical power spectrum which I downloaded from the website. So what I've done here is I've downloaded 3 maps from the Planck website, and I've taken the power spectrum, I've applied this function here, anafast, to those 3 maps, and I'm going to now plot the results. And you can see that the data gives us something which is very, very close to the theoretical power spectrum, which is nice. I've had to apply some scaling factors here, and you can look at those in the code in more detail later and ask me questions if you have any more questions about them. But what's interesting is that this grey plot here, this grey line, is that white noise the white noise of that the power spectra of the white noise array that I created earlier. And you can see that the power spectra of white noise is something which is increasing like k squared. So in white noise we don't have this lovely peak at scales of about 1 degree, and that's why we don't see that structure when we look at white noise, but we do when we look at the CMB. And if I plot that on a log-log plot, you can see that that white noise power spectrum is a straight line as we would expect. And the data fits so the data here has come from Planck 2015 data, and the red line I think is the best fit power spectrum to that data set. So you have to play a bit with some of the scaling factors in order for these 2 lines to match up, and you can look at that in more detail. I'm going to stop there and see there's a few more interesting plots that we can look at if you've got any more questions. But I'm going to stop there and see and see if anyone's got any questions.
Fantastic. So do we have any questions for Karen?
So on the power spectrum of the CMB data, there were these kind of oscillations at the high frequency bit.
Yeah.
Is there an explanation for those?
So they're called acoustic oscillations. So they're created. That's to understand how those are created. You need to go and look at early universe physics and think about how the initial perturbations, which were seeded in the Big Bang, how they would evolve over time to produce the CMB. It's been a few years since I've done that, so I don't remember. But they're called acoustic oscillations if you want to go and have a look.
Any more questions? Do you want to show us these cool images?
Well, there's just one library which I didn't talk about, which is AstroML, which I started looking at, and I think it's been publicised here as well. And so if this is a library that you can start doing machine learning on cosmological datasets, and there's some really good examples here. I haven't had any time to go through some of the examples from this website, but I just wanted to show it in case anyone was interested in going and looking at it further. Okay, thank you.